Okay, so for the next topic, we will talk about offset bits. And as we said, offset bits are usually used to select one byte out of multiple bytes that are on the output of a chip. So theoretically, a chip can actually produce a large line, let's say a word, for example, or two words or whatnot, but you want to be able to select one byte out of that word. And as you know, for example, let's say a word is 4 bytes and you want one byte out of 4, you can use a mux, essentially. And you need 2 bits to select 1 out of 4. Now, what are you what are you using to control the select line? More bits from the system address bus. And theoretically, you can do that, right? So let's take a look at an example here. We have a chip that is 1024 by 32. Let's see what we need to show. Like, how do we actually control the chip and its signals? So first I'm going to draw the chip. Okay, so this is 1024 by 32, which means the output of this chip is 32 bits. Or you can alternatively you can write D31 down to 0. Right, and then it takes 10 address bits. So I'm just gonna write 10 here. And there's a chip enable or chip select, but I'm also interested in selecting one out of these 32 or 8 out of 32 bits or 1 out of 4 bytes. So I can actually pass this to a mux in this case. So this will be a 4 to 1 mux. And as you know, for a 4 to 1 mux, you need to have 2 select bits. So this will be S0 and S1. So you have 2 bits here. And then you have the output here as 1. Obviously, this is 1 instant out of 8 instants. So like you will have actually 8 muxes back to back if you're doing it on a bit basis. And then these select lines will be actually mapped to all these 8 bits. But for simplicity, what we do is we just say it's a 4 to 1 mux, assuming we're working with bytes, and then you just need to pick 1 byte out of the 4. So the question is, where do these select line come from? Well, the answer is they also come from the addresses. So the system address bus has a lot of addresses, a lot of address bits, and we're going to map 10 of those addresses to the address input of the chip. This is the chip select or the chip enable. And we're going to map 2 of these addresses to the select lines of the mux. So usually we start with the lower address bits for the select line of the mux. So this will be your A0 and A1. And then the next 10 are the next up ones. So this will go from A2 to 11, right? What is it? 2, yep, 11. So 11 down to 2. So all in all, I'm actually using 12 bits. So you can ask yourself, like, wait a second, am I doing it correctly? And the answer is yes. You do need 12 bits to access individual bytes in a 4 kilobyte chip. So, but before I go there, let me just recap this idea here. So we have a chip that's producing 32 bits on the output, or 4 bytes, and I want to be able to select 1 byte out of 4. So I need to use a mux, and then that mux is going to take 2 bits for the select lines to be able to select 1 out of 4. And those bits are usually called in offset bits. And then we'll see some other examples where you have offset and chip select and address bits and whatnot. Now, the one idea I was referring to is that all in all, I'm using actually 12 address bits to select 1 byte in a 4 kilobyte chip. So it doesn't matter because an alternative to this would have been that there's no free lunch basically. So an alternative to this whole thing would have been that you're using a 4096 by 8. And for 4096 by 8, you will, okay, I'm just going to quickly do that. Okay, so an alternative to 1024 by 32, you would have used a 4096 by 8 that will also be 4 kilobyte, like 4096 by 8. That's also a 4 kilobyte chip that's producing 8 bits on the output. Now your address bits here are going to be 12 or A11 down to 0. So you still use 12 bits. Just happened that in the previous example, the assignment of these bits have moved around a little bit. Okay. Now the next topic I'm going to mention here is that we can arrange the memory chips to give us a larger or a wider output. So in this example, the chip already has a 32-bit output, and we use the mux to select one out of these bytes. It could be the other way around, actually. It could have been that we have a small chip, and we need to use multiple chips to make a larger output. So, for example, I can use four 1024 by 8 chips to give me that 32-bit outcome, right? So all of them are going to be 1024 by 8, 1024 by 8. Apologize for the tiny font here. Then, right, and each one of them will give me 8 bits. So obviously the first one is going to give me D7 down to 0. The next one is going to give me D8 or to 15, or 15 down to 8. And then this one will give me the next 8, and so on. So this is 16 to 23. Wow, the font here is not coming up very nicely, but you got the idea. And then the last one is 24 up to 31. Okay, and all of these are actually going to be connected to the data bus that is 30 to, again, this was 0 to 7, right? So all of them are connected to my data bus that is D31 down to 0. So I was able to use 4 chips side by side to get a wider output, right? And obviously, all of them in this case, all of them are going to use the same 10 bits, A9 down to 0. And this is going to be fed to all these chips simultaneously. That way, when a given address is selected, 4 chips will be producing their line on the data bus to get that 4-byte output. In fact, actually, chips are used either side by side to get a wider output, or they can be used in a stacking manner to get a deeper address. So just like we did 4 chips side by side to get a 32-bit output, we can actually stack them on the top of each other to get a 4096 by 8. So like we could have them stacked like this, whereas each one of these chips is going to produce 8 bits of data, and then all of them are going to share. So in this instant, I'm sharing the address bits. So this is A9 down to 0. It's going to all the chips, and then each one of them is producing 8 bits on the output. right? And the difference here is that I need to use other bits, for the chip select. So only one chip is valid, or only one chip should be valid at any given time. So this will be A10, A11, 00, A10, A11, 01, A10, A11, 10, and then A10, A11, 11. So I used my addresses A0 to A11 to do two things. One is to select an address out of the address range, and to select a chip out of the 4 chips. And like I said, all these data outputs are connected to my data bus, 8-bit data bus, right? Or I could have stacked them like I showed you in the previous example to put them all side by side to produce a 32-bit value like this. In both scenarios, I have a 4 kilobyte memory system. Now, again, this one, if I did care about the granularity of such that I need to use or select only 1 byte at a given time, I would just feed this into a mux. And then I will have to use 2 bits to select 1 out of the 4 words that are coming from this mux to be read. And for that, those 2 bits are going to be 2 address bits, like A10 and A11, for example. Although it shouldn't go this way. Usually the mux bits are the lower end of the bits, and the address bits are a little bit on the higher order. Okay, so all in all, when I have 4K and I'm comparing apples to apples, if I have 4 kilobyte chip memory system and I have 4 kilobyte memory system, one is going wider output and a shallow address space. The other one is a deep address space, but a narrow outcome. I still have to use 12 bits. Okay, this is a good place to end this here, and I'll see you in the next video.